In system analysis, there are two response functions of a system which are very, very important. The first one is the step response, and the second is the impulse response. So let's define these two response functions. The definition is very simple. We have got a system with input u of t and output y of t. There are two special cases. In the first case, let's put the 1 of t function, the Heaviside function, to the input. So u of t is 1 of t. In this case, the signal that we can measure at the output of the system will be the step response. In this case, y of t is equal to v of t. So the step response is important function. That's why we have another separate notation for that. So in that case, the y of t is v of t. So if the input is 1 of t, the output is y of t. So we can do these measurements quite easily because the 1 of t function generation is very, very simple in the real life. So it's very simple to measure the v of t, the step response of a system. The second special case, if the input function u of t is the Dirac delta function, the Greek letter delta of t, in this case we can measure a special function in the output of the system, and this will be the impulse response function. And it's also very important, that's why we are going to use a separate letter for that, wt. So in this case, y of t is equal to wt. Wt is the impulse response function. In many books, we use wt. In many books, you can find h of t or g of t. So it's also the same. Wt is for the weighting function, because this impulse response function we sometimes call weighting function. Why are these two functions so important? In the next video, we are going to see that if we know v of t or w of t, we can calculate the output for any input function. So this is why we need the step response or the impulse response. So usually we say that v of t or w of t characterize the system, because if we know these functions, we can obtain the output for any input function. So the measurement of the impulse response function is difficult. Difficult because in the real life we cannot find a Dirac delta function. So the measurement of Wt is difficult. Fortunately, we have got a direct connection between the two functions. We have studied the delta t is the time derivative of 1 of t. We studied it in the signals block. This is why this connection is valid for the output signals too. So Wt is equal to the time derivative of v of t. So the impulse response function is the time derivative of the step response function. But in the future, in the next video, we are going to use the impulse response function Wt. We need Wt. We need Wt to characterize the system. And this is why we need it. We need to measure it. But in real life, we cannot measure it. But a normal question is arising. How to get Wt if we cannot measure it? So according to this direct connection, that is Wt is equal to the time derivative of v of t, and the measurement of v of t is very simple because the step function generation is easy, so we can measure it. If we can measure it, The next step is to take the time derivative of v of t, and we have w of t. And we can use w of t as the characterization of the system. So usually this is the first step, and this is the second step to get the w of t. Of course, delta t can be approximated, but if we approximate the delta t, we get an approximated w of t. It's not in many cases, it's not the clever way. A better way, if it is possible, to use 1 of t to get the step response and then the impulse response from that. So in the next video, I am going to present you a technique. It is called the convolution, why w of t is so important for us.